Hi, my name is Kevin McPeak. I came to Louisiana from Switzerland, where I did my postdoc for 5 years in Zurich, and then I moved here in fall 2015, starting as an assistant professor in the chemical engineering department. My laboratory works in the field of plasmonics. So plasmonics is this idea that if I take a metal structure, which we typically think of being as reflective, like the mirror in your bathroom, right? Well, if I take that metal structure and I make it really small into a nanostructure, rather than being reflecting, these small metal structures actually absorb light or scatter light very, very efficiently. And we can do things with that. So we can use these small metal nanostructures to capture a light very efficiently and augment the performance of a solar cell. Or we can use these small metal nanostructures as sensors for detecting if small objects attach to them, like in biological sensors. In my laboratory, we use them for catalytic purposes, so for actually treating water. We also use them as a way to better understand how proteins fold, right? So proteins can either behave well and fold correctly, or they can misbehave and misfold. And this can lead to many diseases, some of them Parkinson's, Alzheimer's diseases, most notably. And so we're working on ways of using these metal nanostructures for understanding in situ how these proteins are folding or misfolding. On the catalytic side, we're using these metal nanostructures to treat water, right? But rather than treat water with ultraviolet light, which is how it's typically done from the sun, which is only 5% of the sun's power, we want to use the visible portion of the spectrum, which is 43%. So our metal nanostructures are tuned to the visible portion of the spectrum, where we can take advantage of more power from the sun.